In this lecture, we introduce the chain rule. We've learned the basic derivative rules and can now differentiate power functions and polynomials, trig functions and exponential functions. But still, most functions are beyond our reach. We can differentiate e to the x and x squared plus 2x, but what about e to the x squared plus 2x? How does one differentiate a composition of two functions? Most functions, such as y of x is e to the x squared plus 2x, are compositions of simpler functions. For example, if f of x is x squared plus 2x and g of x is e to the x, the composition function, g composed with f, is the function y of x is e to the x squared plus 2. And if we compose the functions in the opposite order, say f composed with g, or f of g of x, we get the function y of x is e to the x squared plus 2 e to the x, or e to the 2x plus 2 e to the x. In this case, f composed with g and g composed with f are different, but they're built out of the same idea, the same basic functions, e to the x and x squared plus 2x. After we've learned a set of basic building blocks to differentiation, we need the chain rule to put them together and to allow us to compute the derivatives of functions like e to the x squared plus 2x, which involve function composition. We can create a method for differentiating a composition of functions based on the derivative of the various functions in that composition. So if y is a composition of two functions, say y of x is g of f of x, then we can treat the inside function, f of x, as an independent variable and first compute the derivative with respect to that new independent variable, I'm calling it u here, and then when we're done, we can compute the derivative of u, the new independent variable, with respect to x. If we do that, then the derivative of my original function with respect to x is the derivative of the function with respect to u, the intermediate variable, times the derivative of u with respect to x. We motivate this formula by noting that this rule appears reasonable since the differentials du appear to cancel out in this fraction, and this can be made more precise using limits. The chain rule is this: the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. Let's do some examples. If y is e to the x squared plus 2x, let's think of u as this inside part as x squared plus 2x. It's a variable in its own right, and the derivative of e to the u with respect to u is just e to the u. So the derivative of y, this function in front of us, with respect to x squared plus 2x, with respect to u, is the derivative of y with respect to this u is e to the x squared plus 2x. The derivative of e to the u is e to the u. But what about dy dx? We wanted not the derivative of y with respect to u, but the derivative of y with respect to x. And so dy dx is going to involve multiplying by the derivative of this inside part, by the derivative of x squared plus 2x. What's the derivative of x squared plus 2x with respect to x? Well, that's just 2x plus 2. So to recognize that we really want to treat x as the independent variable, we need to multiply by this 2x plus 2. So our final answer is, if we're differentiating y equals e to the x squared plus 2x, the derivative is e to the x squared plus 2x times 2x plus 2. This product here came into the problem because what's in the exponent of e is not simply x. It's more complicated. I often think of the chain rule as involving a new variable, some expression of x. In this case, y was e to the x squared plus 2x, and I treated that term in the exponent, x squared plus 2x, as a variable in its own right, and I took the derivative of it with respect to that variable. So I computed the derivative of e to the x squared plus 2x with respect to x squared plus 2x, and that answer is e to the x squared plus 2x. But my variable is not really x squared plus 2x, so I wake up, so to speak, and realize that this x squared plus 2x is not my independent variable, but x is. And so when I'm all done with the first step, I have to correct for this by multiplying by the derivative of the new variable. The derivative of x squared plus 2x with respect to x is just 2x plus 2. So that's the reason, again, I'm repeating the problem, but that's the reason we got e to the x squared plus 2x times 2x plus 2. Let's do another example. Suppose I want to differentiate e to the x squared. We don't have a rule for differentiating e to the x squared, but we do have a rule for differentiating e to the x. So we want to take the derivative of y with respect to x. I'm going to think of x squared as a variable in its own right and ask, do I know the derivative of e to the u with respect to u? And the answer is yes. The derivative of e to the u is e to the u. Then I ask, do I know the derivative of x squared with respect to x? Well, yeah, that's 2x. I have yes in both cases, so I can put them together. If the derivative of e to the u is e to the u, and if the derivative of x squared is 2x, then if y is e to the u, which is e to the x squared, then my derivative will be the derivative of y with respect to u, that's e to the u, or e to the x squared, times the derivative of u with respect to x, which is 2x. So I get e to the u times 2x, or e to the x squared times 2x, or cleaning it up a little, I get this answer. Let's do a few more examples. Suppose f is g composed with h. Then the chain rule says the derivative of f with respect to x is the derivative of g with f stuck in it times the derivative of f. For example, if f of x is the tangent of the square root function, then f is a composition of the square root function is on the inside and the tangent function is on the outside. So it's a composition of the tangent function and the square root function. So the derivative of the tangent of the square root is the following. Well, first off, what's the derivative of the tangent function? Secant squared. But wait a minute. Inside the tangent function, do I have just x? No, I have a square root. So now I need to multiply by the derivative of the square root. Now the square root is x to the 1/2, so the derivative is 1/2 x to the minus 1/2. If I clean that up a little bit, I get this answer. So the derivative of the tangent of the square root is the secant squared of the square root divided by 2 times the square root, all according to the chain rule. Or, let's make it slightly more complicated. Let's take the derivative of the tangent of the square root of x squared plus 4. When I look at this, my first question is, this is the tangent of something. Do I know the derivative of tangent? Well, the tangent of x has derivative secant squared x. Now, in this case, inside the tangent function is the square root of something. Do I know the derivative of the square root? Well, the derivative of the square root of x is 1/2 x to the minus 1/2. But inside the square root is x squared plus 4. Do I know the derivative of x squared plus 4? Yes, it's 2x. So f is the composition of functions on the far inside is x squared plus 4. Moving a little bit outside is a square root function, and on the very outside is a tangent function. So the derivative of the tangent of the square root of x squared plus 4 is the secant squared of that stuff times 1/2 that stuff to the minus 1/2. There's my derivative of the square root function. But wait a minute, were we taking the square root of x? No, we're taking the square root of x squared plus 4, so multiply by 2x. And so my derivative is secant squared of that square root times 1/2 of that thing to the minus 1/2 times 2x. We have chained these together. The derivative of the tangent is secant squared. The derivative of the square root function is 1/2 something to the minus 1/2. The derivative of x squared plus 4 is 2x. And then a little algebra cleans it up. In the next presentation, we apply the chain rule to the power rule to get a new version of the chain rule.